Hello everyone and welcome to next discussion on introduction to groundwater hydrology under this groundwater engineering course. As we have been discussing about zone of aeration and vadose zone, here also we can see all these zones on this figure, that the top part we consider as zone of aeration because some pore spaces are filled with the air also or some other gases. So, that is it is not saturated, whereas zone of saturation is saturated with water. So, you do not have anything except the rocks or sediments plus water. So, that is why it is called zone, the top part is called zone of aeration, zone of saturation, and between the imaginary line which is there, which is called the groundwater table or groundwater surface also. Whereas ground surface is generally undulated, and normally it is assumed that water table is flat, but depending on various geological conditions, it is not necessary all the time that we may find water table as flat, though it is shown here as flat. Now, this the other part also we say this is the suspended water or vadose zone. In this part, the top part above the water table, and there is a, now if we divide this zone of aeration, then three sections are there. One is the top part is the soil water, which is soil. So, generally you get soil of 1 meter, 1.5 meter, maybe less also. So, that water is there, basically the moisture where the organic or plants grow. So, that water is there. Then another section is the pellicular water is there, root zone and other things can also be there, and then capillary water just above the water table. So, this kind of divisions in subsurface conditions are there. So, the form and configuration of zone of aeration is basically controlled by topography and geology and other conditions like climatic conditions, drainage and vegetation, and all these are which controls overall influences the position of water table. Let me explain here a little bit. Like as said in the previous lecture also, that in pre-monsoon conditions the water table may go down because the water has been exploited, and now zone of saturation will reduce, whereas zone of aeration will increase. But in case of post monsoon condition, the water table may go up. So, that is why the weather and climatic conditions, rainfall and other things influences the water table, not only geology, not only topography and largely. So, like in a particular area, the geology is not changing frequently or seasonally, the weather is changing, and in a large time window we say climate is changing. Topography is also not changing, but because of some human interventions, in some regions the topography may change, and that may change the position of your water table. So, that is why we keep all these things in the category of influencing water table, that is topography, geology, climate, drainage and vegetation. Drainage is also. So, in monsoon season your streams are having water, and therefore, they might recharge the groundwater regime, and which influence the water position of water table. Whereas, in summer months many which are not perennial streams water may go down, water table may go down. So, that is why drainage also controls the water table. So, in topographic highs, where like in Himalayan conditions or mountain condition, hilly region where the topography height is there, highly permeable formations are there, and arid climate and drainage divides where watershed boundaries. So, there we get less water, but in the lower areas like topographic lows and maybe low permeable or high permeable conditions and climate and drainage divides or not drainage divide, but other parts of a watershed we may get different water conditions. So, water bearing and water yielding characteristics in vadose zone, and that is the top part, above the water table, that zone control the percolation of water to the zone of saturation. Now, there are two things. One is the infiltration from water, from surface water to groundwater, and then percolation. So, initially what happens, whenever there is a rain, the initial process will start, which is the infiltration, and later on when that infiltered water goes downward in a pellicular zone or capillary water zone, then that process is basically percolation. So, there are two different things. First infiltration occurs, then percolation occurs, and which makes the zone of saturation rich, and water table may go high because of better percolation of rainwater. So, and this may range between 0 in outcrop area of water table, and where water table, outcrop areas of water table means springs, where water table is exposed because of particular topographic arrangements. So, this may range between 0 to 100 of meters in arid climates, in upland regions underlain by highly permeable formations. So, these are the important aspect in case of vadose zone and saturation. Vadose zone or zone of aeration may further be divided, as we have seen, the soil water, pellicular water, and then capillary fringe water. So, where capillary actions can also take place. So, these are the, so if we go in detail about the soil water, then it comprises the zone which is immediately below the land surface, and which soil moisture is available for plant growth and for direct evaporation to atmosphere. So, this part is very, very important. Where soil thickness is less, then the groundwater scenario also changes, and where soil thickness is more, then the groundwater scenario again will change. So, soil water, when we say soil water means basically we are talking about the soil surface, which is just ground surface, and soil surface means it is having the materials rich with organic content. So, plants and plant roots and other things, and basically plants grow only in that part of the earth or top part of the surface, which where the soils are there. And also evaporation, also maximum evaporation either occurs from open water bodies, which is the maximum, and then next evaporation occurs from the soil surface, because soil surface is having moisture, and whenever it is the situation, then the evaporation to the atmosphere. So, that we can consider in some from some sense a loss of water to atmosphere from soil surface from groundwater perspective point of view. So, evaporation from soils and transpiration by vegetation cause large variety to moisture content from porosity levels to below wilting or weak point levels. Now, the point here is that because if there are soils, it is likely that we will have vegetation. Now, the overall loss to the atmosphere of water would be in the form of both evaporation and transpiration. So, a combined word we use is evapotranspiration. Now, whenever the temperature conditions are favorable, then the moisture in the atmosphere or the loss of water to atmosphere is very large. Like in monsoon season, when heat is there, moisture is there, so lot of humidity occurs. So, this water gets from liquid state to gaseous state, and it creates very uncomfortable condition, but overall it is a loss of the water. Now, this soil water, that is wilting point level, which a term which we have used, that is the minimum amount of water in the soil that plant requires not to wilt, means not to die. So, that minimum amount of water, that minimum amount of, you can say, a minimum amount of moisture which is required for sustainability of water, that is called wilting point levels. So, if the soil water content decreases, that means the moisture decreases to this or any lower point, a plant wilt and plant will die, basically can no longer recover its turbidity when placed in a saturated atmosphere for 12 hours. So, an example is shown here. The first one on the left side is saturated with water, then because of gravity flow the water comes out from the pot, then the field capacity is there, then the evaporation is happening or transpiration is happening as you can see here, then whatever the available water which is also being lost and wilting point is reaching, because no more water has been added here, and slowly then wilting start taking place, plant is going to die, and after some time if water supply is not there, moisture is not there, this is what the result is. So, water plays very important role for the survival of plant. Now, second zone which is the pellicular water, which is the most of the time water in vadose zone is held against gravity. So, in capillary interstices and in thin films over the surface of the grains due to strong molecular attraction of solid particles to the solid or liquid interstices. What happens when there are gaps and capillary tubes, natural capillary tubes are generated, then the movement of water occurs, and generally this water is from bottom to upward side occurs, because the top part is getting unsaturated, the lower part is having some more moisture. So, from higher to low moisture areas it goes, and this is called the pellicular water. This is for the system, for entire system of water, groundwater, surface water, soil water, this is also very important. So, pellicular water zone lies between the soil water, the top part zone, and the capillary water which is just below of the pellicular. That is the pellicular I have already marked here, and then temporarily water moves downward in this belt as gravitational water. So, water may go like this, or because of capillary action sometimes in special conditions water may go up also. So, this is a very important part of that section of subsurface conditions or subsurface zone. When the soil is saturated, like it happens in monsoon season or over irrigation, and recharge occurs, the entrances may filled with water to saturation capacity, and they may revert to retention capacity after complete drainage. So, this is what happens, when soil are saturated, then recharge will occur, and that is why it is important to know that when the really groundwater recharge can get benefited or groundwater can benefit, the first condition is that the top part has to be saturated, and it can happen if there is continuous rain, maybe slow rain, and in monsoon season in most of the areas like in India it happens. Now, water moving under gravity through large interstices or large pore spaces or fracture zones may reach the water table faster if openings are large, the grain sizes are large, then in between the spaces are large, interspaces are large, and the permeability is there, high permeability, high porosity is there, then water will move faster to the ground, moving through small interstices as well. And due to all this, the moisture content may differ at different places within the vadose zone. It is not necessary. See, you cannot assume that either on surface or subsurface the geological conditions are same throughout, not at all. Almost every 5 meter, 10 meter, or even suddenly the geologic conditions may change. So, therefore, it is for if at one place I am getting water, but maybe 20 meter away from that place I am not getting water. So, this might be because of geologic conditions. So, that is why this it cannot be assumed that everything in subsurface condition and is smooth and like layers as I have shown earlier, that like these layers. No, this is just schematic, this is representation of the thing. The real situation is completely different in natural conditions. But overall this is how one can understand. Then the third section of zone of aeration is capillary fringe water, where this water where the zone overlying the water table, top of water table, in which water is drawn up from the zone of saturation through capillary action and held against the force of gravity in all of the rock interstices is called capillary fringe. Now this those sounds very small, but it is very important in certain conditions. Let me give you an example. You know, in large parts of Punjab and Haryana, and you know, the intensive irrigation have been done in past, and that means the this zone of aeration, especially the capillary fringe water, this water, the soil in this part of the subsurface conditions was fully saturated, and this has brought because of capillary action, it has brought water more on the surface, and that water was evaporated, but the water which was carrying salts and other things, alkaline materials, they got left on the surface of the earth. So soil salinization, soil alkalization occurs because of capillary fringe water. So this is another very important thing, that a balance has to be struck, that all the time the water should not go up, otherwise it will bring the dissolved salts, and after evaporation the dissolved salt may remain on surface, and then these soils becomes completely not fertile. And this phenomena or this sort of hazard has occurred in many parts of India, especially in Punjab and some parts of Haryana, because of over irrigation. So the phenomena, because drainage system was also not available. If drainage system is there, then this salt and other things will go away, but drainage system was not there. So the whatever the loss of water was happening, it is because of evaporation, but the salt remained on the surface and created problems. Now some solutions people have developed, adopting, and developed also some drainage systems to resolve this issue. So phenomena of water rising through tubes or capillaries of small dimensions, which we call capillaries, against the force of gravity are known as capillary fringes. This plays very important role, example I have just given, and this happens due to the surface tension in water and adhesive forces exerted by the walls of the tube. So the tubes are so tiny, so that the surface tension in the walls of tubes help the water to go up. Now in capillary fringe water, and the height of capillary rise of water in rocks is related to dimensions of the voids. Size matters. So if the fracture is large, then capillary action will not take place. So it has to be tiny, and cleanness of the walls of the interstices. If fractures are rough inside, then capillary action might not take place. But in soil conditions, these possibilities are there, where clay materials are there. Soil generally are having lot of clay, and clay can create smooth walls, and those walls helps the capillary water movements, and temperature and mineral content I was mentioning, or salt which I was saying, they play a very important role. If they are left because of evaporation of water, they are left on the surface. So for which the density of course depends, and the relative altitude of the rock where the capillary phenomena are operating. So generally in a low lying area, this phenomena may occur in a large way, whereas in higher areas within a same area may occur in a less manner. Whereas in case of sedimentary rocks, the height of capillary fringe depends on the size of grains. If it is fine grained, there are chances of capillary action. If it is coarse grained, that means voids may be coarser, the walls may not be smooth, the capillary fringe of tubes will be larger, then things are completely different. And their assortment means how whether the grains are well sorted, poorly sorted, and so on. Whereas in fractured rocks, rise is determined by the size of opening joints and size of sorting of filling materials. So depending on lot of geology plays very important role in case of groundwater. never forget that is very, very important, because it is not just stored there as a tank. Water is not stored in subsurface condition as a tank full of water. No, it is stored within the pore spaces, fracture zone, weathered zone, and that is what we keep exploiting. So, the width and thickness of zone of saturation, this next part, this is zone of saturation, that may be small in areas underlain by massive rocks. Massive rocks means here that rocks which do not have fractures or weathered zone, and with shallow fractures and weathered layers of thousands of meters in areas underlain by thick sequence of sediment. So, again depending on sedimentary rocks or depending on the rocks, their arrangements, and the possibility of getting a thick zone of saturation or thin zone of saturation will depend. So, like here the example is given, like it is a granitic conditions or igneous conditions are there. So, the zone of saturation which is shown as a blue part here, which is what is saturated, the lower part which is shown as a light pink color is where you do not have much fractures and no water is available. So, in the previous discussion I was saying that if I create a bell, which goes here and rest is my sealed part of my bell, then I will not get water here. So, if I want water, then either I should go to here or remain here, then I will get water. So, I should struck only the zone of saturation, then I will get the water in my tube well. Otherwise, if I go in deeper always does not mean more water. That this is the point which I wanted to bring here at this stage. So, there are two zones of saturation in some areas depending on the geological condition, topographic conditions. One is the where there is a permeable layer in vadose zone, and a downward movement may retarded, resulting in the saturation of intersects and formation of a purged aquifer above the impermeable. So, here one condition is there that water table here which is shown, the saturated zone is shown with blue water or blue color and rest is not saturated, but in between you are having conditions that part is saturated. So, if I dig a well in that part, then at a very low depth I can get water, whereas in normal conditions I get water at this depth, and in a purged water table conditions I may get water at this depth because the spring is coming out. Is a special topographic arrangement where water table is cut by the topography. So, I may get a spring here, and because of this purged water table only a small zone is there where the saturated zone is there, from where I get the water. So, in many conditions, geologic conditions, these things may be there at all, but finding only this purged water table which is a small portion in subsurface condition is not easy. So, generally people will always try to find a large part of saturated zone, so that the pump or the well will keep supplying water round the year. Now, as we have discussed, according to origin source subsurface water can be classified also. So, other way we have classified, some people would like to classify water based on origin and source. So, there is a connate water, that water entrapped in the interstices of sedimentary rock at the time it was deposited. At the time of sedimentary formation, the connate water, the water which is trapped is called connate water, whereas meteoric water is derived from atmospheric precipitation, and then other water also, the magmatic water and juvenile water. So, generally it is not these kind of waters are not very commonly available or commonly struck, but if they get, then generally for maybe in certain conditions may be fresh, otherwise these are generally saline water. And last one in this category is the volcanic water, which is derived from heat and chemical activity of volcanic. Some of these I have already discussed in previous discussion. So, where one or more purged aquifers are found, the water table below and the lowermost zone is called the main water table. So, these water tables which are in the purged zone will not be called truly a water table, only this will be called the groundwater table. Further, the groundwater is discontinuous. This I have been emphasizing, keep emphasizing. This is basically an imaginary surface which is just above the saturated zone. Now, the rocks are not uniform simply in form of layers underneath, under the surface, not at all. There are a lot of variations are there in terms of thickness, in terms of types of rocks, in terms of fractures, joints, weathering. So, water table is discontinuous surface, not continuous. In fissured consolidated rocks in which large unsaturated blocks of rock may separate water with saturated fissures, and this is a very common thing, especially in hard rock terrain. So, if I just compare in Indian conditions like Indo-Gangetic plain, where we can not more continuous, not fully continuous, but more continuous water table you may find in a large area in Indo-Gangetic plain. But if you go in hard rock terrain like in South India or in Bundelkhand or other parts, then the water table are very localized kind of thing and definitely discontinuous. Whereas in the terrain which is full of limestone, which we say karst terrain, the water table may be virtually an open water surface, but in subsurface conditions because of caves, cavities and other things. So, the finding water in a limestone terrain is a very challenging task, because conventional methods of understanding the position of water table will not work in limestone terrain or karst topography or karst terrain. So, one has to be little careful about. This is the example given. In the karst terrain, the water table may be virtually an open water surface. So, here as shown here, the water table in these caves, you are seeing the water is there, but the top part is completely, this part is completely empty. These are the caves which you are finding, and some caves might be interconnected, and you may have the sinking stream. So, some stream suddenly disappears and it will saturate the in subsurface conditions. So, this is the limestone pavement and the sinking, dolomite, sinkholes, all these things are a common thing in limestone terrain, and lot of subsidence occurs, surface subsidence occurs in a limestone terrain because of the movement of water, and water can dissolve the calcium carbonate easily. That is why these cavities and caves are formed in a large form. So, we are basically reaching to the summary of or last discussion of this particular lecture is that in karst terrain the water table may be virtually an open water surface, and the position and existence of water table will definitely depend on topography, geological structures, area of recharge and discharge of groundwater. So, for basically what I am trying to say that for each and every geologic conditions or geographic locations, the geology, topography, which are the areas which are recharging the groundwater regime, which are the areas where the groundwater is getting discharged, all are important, and the rocks which are present in subsurface conditions, that is their porosity, their permeability, and how much water is being withdrawn or utilized. So, the availability of water will depend on availability of groundwater will depend on these many factors. So, water table in many places is a subdued replica of the topography, many places mainly in hilly regions, where the water table follows the topography generally. But if there are fault or thrust or fracture or that kind of thing, dike and other things, then it might not follow. And like in Indo-Gangetic plain, so water table may again follow the subdued replica of topography, which is almost we can consider almost flat. It is not exactly flat, but relatively compared to hilly regions or Himalayan conditions, it is almost flat. And therefore, water if in a Indo-Gangetic plain, if you get water at one place at 10 meter, and if you go 50 meter away or 100 meter away, it is highly likely that you may get water again at the same depth. But in a hard rock terrain, this possibility may not be there at all. The similar conditions may not exist even in a small area. So, generally water table tends to be more uniform in flat terrain. I have given example of Indo-Gangetic plain and rocks of high permeability. Rocks of high permeability means sedimentary rocks, mainly we are talking of large grain size. These rocks may provide you a uniform water table, and if they are located in a flat terrain. And in generally the deeper in uplands and shallow in valley bottoms. So, in Himalayan conditions or in a hilly terrain, if you are looking for water, then the water table will be much deeper in at the top of the hill, but if you go near to the valley, then you may get water at very shallow depth. So, that may help you if somebody is looking or trying to locate a suitable site for a tube well. Then do not dig from the top or top of the hill, go near the valley. It is highly likely that you will get the water. So, this brings to the end of this discussion. Thank you very much for your attention.